In this video, we will be looking at some word problems that represent exponential growth. So we're going to start off with a little question where we discover what the graph would look like, what a table of values would look like, and what the equation would look like. So here's an interesting pay system. I pay you a penny on the first day, 2 pennies on the second day, 4 pennies on the third, and I just keep doubling the number of pennies each day. How much money would you get on the 30th day? So we're going to start off by continuing the pattern so that we can sketch the relationship. So you get $0.01. A day has passed, you get double that. So you get 0.02. We double that, and we're now at 0.04. We double that, we're at 0.08. We double that, 0.16. Then 0.32, and then the pattern continues. Now, I'm not going to sit on my calculator and multiply by 2 until I get to the 28th, 29th, and 30th day. Instead, I'm going to think about how I got each of these numbers. To get 0.04, we took the original 0.01, it got multiplied by 2 to get day 1, and it got multiplied by 2 again to get day 2. Which means on the second day, 2 was multiplied twice, but that can be written as 2 to the power of 2. And then when I multiply by 2 again to get to 0.08, that means I could have just done 0.01 times 2 to the power of 3, because that will be the third time I double my answer. This was the first, the second, third. For the fourth day, I've now multiplied by 2 4 times. So it'll be 2 to the power of 4, and then with that original 0.01. So with that pattern, on the 28th day, I should take the original penny and multiply it by 2 28 times. And if I do that, I get 2, 6, 8, 4, 3, 5, 4.56. And that's dollars. So on the 28th day, you'd be getting millions at this point. Then now I can double it again, or do 2 to the power of 29 times 0.01, and we get this time 5,368,709.12. And I double one more time, and now I'm at 10,737,418.24. Now, what we looked at before with exponential graphs is that we should have a common ratio. And if I were to take these y values and divide them, I should get 2, because we're multiplying by 2 to go from number to number. So if I were to divide those numbers, it would only be logical to get 2 each time. Okay, so that just justifies that this is an exponential question. But now I'm going to start my sketch. So on the x-axis, we have number of days passed. And on the y-axis, I have amount of money in dollars. Now I'm not going to sit here plotting each point, because plotting 0.01, 0.02 is going to be quite hard on a scale that needs to reach the millions. So all I'm going to do is say here's 0.01, and I'll say on day 30, the very top here, that's going to be the 10,737,418.24. And you'll notice at the beginning when we double, it's very gradual. Even on day 5, we've barely moved. So let's say day 5 is here. We're at 32 cents. So that's not going to look like much of a change. On the 28th day, we're in the millions. So it does look like it's going to be a gradual increase, and then it's just going to skyrocket. And there we are. I labeled the start and the end of this scenario just to get a general sketch going. And we already know what exponential functions look like, so I know this will be a decent shape. Now for the domain. State the domain and range of this relationship, assuming you stop at the end of the month. Now, for a regular exponential graph, the domain would be infinite. However, because we do have a start of day 0 and an end of day 30, that's our domain. Our range is usually from 0 to infinity, not including 0 because there's an asymptote there, which there would be in this case as well. However, our starting value is 0.01, and the highest we get is to that 10,737,418.24. So that's my range. The domain and range for word problems are different because we have to take the scenario into consideration. Okay, let's try to state a function to represent this relationship where x represents the number of days passed and y represents the amount of money. If we just look at our table of values to see how we got these values here, it looks like we took the 0.01 and we were multiplying by 2 for how many days have passed. So 0.01 times 2 to the power of x days. So instead of doing 2 times 2 times 2 x times, we can show it in that exponential form. All right, if the amount of money were to triple instead of double, how would the graph change and how would the equation change? Well, if we're tripling, I would expect the graph to have a more drastic increase, so it would kind of look steeper in a sense. And how would your equation change? Well, instead of having 2 to the power of x, I'd have 3 to the power of x. If the amount of money were to increase by 25% instead of double, how would the graph change? Well, when you're doubling, your increase is 100% increase. You have the actual original amount plus that amount again, which means you're increasing by 100%. So if I'm increasing by 25%, that's less. So I would expect a smaller increase in the function. So it would be less steep, maybe a little flatter on the incline. And how would the equation change? So the penny at the beginning is not changing, but this part here has to change. So when you are increasing something by 25%, if we think about a long process, I would take 25% of that number by multiplying it by 0.25 and adding that on to the original amount. But instead of doing it in a two-step process, I can just do my calculation all in one go by multiplying the original number by 1.25. The 1 will take care of having the original amount, and the 0.25 will add on that 25% increase. And there we are. So here's our first example with no real foundation of how to create the equation, but we did by observing that repeated multiplication of the 2 and thought about how it would relate to an exponential form and that equation. So let's summarize it. We will see exponential growth examples where you're given the growth by a factor like doubling, tripling, that kind of thing, or a growth by a percentage like a 25% increase or a 10% increase or whatever it might be. So if it's growth by a factor, here's what our equation will look like. And we saw this in the previous example. Y equals A, where A is the initial amount, so the starting population or the starting value, whatever it might be, times that growth factor, whether it's 2 for double, 3 for triple, 4 for quadruple, whatever it might be, to the power of how often that growth factor is applied. Now, in our example, it was just to the power of x, the number of days, because the growth factor was per 1 day. But if you have a growth period of, let's say, doubling every 3 days, then I have to put that 3 in the denominator. So here we have time divided by growth period. And if you do that, in a certain time period, you'll see how many times that growth factor is applied. For example, if I said the growth period was every 3 days, and I want to know the final amount in 6 days, it wouldn't make sense to me to multiply the base 6 times, because in 6 days, that growth wouldn't occur 6 times. the growth occurs every 3 days. So 6 divided by 3 is 2. So we're multiplying by that growth factor 2 times for that 6-day period, or whatever units we have. Likewise, if we have growth by a percentage, we still have a for the initial value. We still have the same exponent where we're doing time divided by growth period. But for our base, because we're not given that double, triple, and we're given a percentage instead, you take 1 and you add in your growth value, like we did with the 1.25. So let's look at a couple of examples. And we're going to start with one where I do give us the equation. The fish population in Exponent Pond can be represented by the equation P at t equals 80 times 1.12 to the power of t over 4, where t is the time in years. Explain the meaning of each part of the equation. Well, the starting number should represent the starting, in this case, population. So the initial population is 80 fish. Now, inside the bracket is going to be our growth. I know this is growth because the base is greater than 1, and this is growth by a percentage because I see 1 point something. And it's 1 plus 0.12. That's where 1.12 comes from. And 0.12 is 12%. So we have 12% growth. But how often is that growth? I take a look at my exponent here. We have the years divided by 4, which means a 12% growth every 4 years. So if I were to find the population in 20 years, that 12% growth is happening 5 times, because 20 divided by 4 is 5. So we'd be multiplying by 1.12 5 times, not 20 times in that 20-year span. Okay. Let's try one where I give you the information and you have to create an equation in return. In 2005, there were 85 rabbits in Mulock Park. The population quadruples every 8 years. Write an equation to model this scenario. Well, first of all, I'm going to need variables, and then I'll write my equation. We're dealing with population, and for time, we have years. So I'm going to say, let P represent rabbit population. I could have also used R for rabbit instead of P for population. And let T represent time in years. I'm going to use my function notation. So P at T equals, the initial population is the 85. We're quadrupling, so my base is 4. And we quadruple every 8 years. So that means in my exponent, I'm going to have t divided by that growth period of 8. Now that I have my nice equation, I'm ready to answer some follow-up questions. How many rabbits are there in 2020? Well, in 2020, how many years is that since 2005? So I'm going to subtract. That's 15 years. So I'm going to find P at 15, not P at 2020. And actually, that reminds me, I should add a little bonus here to my let statement. It shouldn't just be the number of years. It should be the number of years after 2005. All right, now P at 15. I'm going to have 85 times 4 to the power of 15 over 8. Now, I recommend you punch this into your calculator all in one go so that you don't lose any accuracy when you divide that fraction, for example. And when I punch this in, 85 times 4 to the power of 15 over 8, and just a quick note, based on your calculator, you might have to add an extra set of brackets for that exponent. I didn't talk about rounding, but logically, I shouldn't have a decimal of a rabbit. So I got 1,143.6. I'm not going to write that because I can't have 0.6 of a rabbit, so I'm just going to round that up to 1,144. And then I'll write my therefore statement. Therefore, in 2020, there will be approximately 1,144 rabbits. Okay, when would there be 21,760 rabbits? Okay, this is the opposite. Instead of being given time, we're given the population. So I'm going to replace P at T with 21,760. And now when we look at this becomes an exponential equation, which we have done before. So first thing we want to do, I see a number in front of my base, so I'm going to divide both sides by 85, and I get 256. And luckily, 256 can be written with a base of 4. 4 to the power of 4 is 256, so I can swap that out. And then I'll rewrite the right, 4 to the power of t over 8. And now that my bases are the same here, I can set the exponents equal to each other. 4 is equal to t over 8. And now I can do a quick cross multiply, and I get that t equals 4 times 8, which is 32. That means in 32 years after 2005, so in 2037, there will be that many rabbits. In 2037, there will be 21,760 rabbits. So this is a nice full type of question because you had to do let statements, you had to create an equation. There was one question where you replaced time with a certain number, and the other where you replaced population with a certain number, and that caused you to actually solve an exponential equation. Let's try one more with growth as a percentage this time. In 1985, there were 285 people with cell phones in the small town of Mathville. So there's my initial population. This number increased by 75% every 2 years after 1985. How many people had cell phones in Mathville in 2000? So here the question goes straight to a calculation. I am still going to write an equation to begin with, and then I'll go from there. And I'll write a generic equation. I'm not going to use that 2000 right away. Now I can use nice variables. I can use x and y. I'm going to do the full process here with let statements and everything because it should be helpful. So we're dealing with people and years. So I'm going to say let P represent number of people and let T represent number of years after 1985. So the initial population was 285. We're increasing by 75%, which means for that base, I'm going to take 1 and I'm going to add 0.75. So I'm taking that 75% and dividing it by 100 to get 0.75. I add those up, and there's my base of 1.75. And this rate is every 2 years. So I'm going to go to the power of t over 2. And now with that 2000, that means time has to be 2000 minus 1985, which is 15 years. So we're looking 15 years later, what is the number of people with cell phones? So P at 15 equals 285 times 1.75 to the power of 15 over 2. And again, I'm going to punch it in all in one go so I don't lose accuracy. And I'm going to round to a whole number because this is people. So that means in 2000, approximately 18,951 people will have cell phones. Predict in what year the number of cell phone users surpassed 1 million. So now we're being given the number of people, which means we're going to replace P at T with 1 million. And it does become an equation again. So I'm going to divide both sides by 285. I don't get an exact value, so I am going to lose a little bit of accuracy. I'll put a few decimals. And now when I look at my bases, these aren't common numbers where you would know right off the top of your head what a common base would be. So when this happens, it's going to be a little bit of a guess and check strategy. Whatever base we have from the growth, that's what we're going to try to get. So I'm going to try to rewrite this number as 1.75 to the power of something to give me 3,508.77. So it's going to be guess and check. So maybe I try to the power of 10. Let's see what happens. 1.75 to the power of 10, and I got 269. Not even close to 3,000. Let me go higher. Maybe I try 15. 1.75 to the power of 15 got me to 4,421. I'm getting closer, but now this is too high. So let me try 14. Now I'm too low. 1.75 to the power of 14 is 2,526. So I'm actually going to try a decimal this time. Let me try 14.5. And I got 3,342. Closer. I'm going to try 14.6. I got 3,534.7. It's not perfect, but it's close enough. So I'm going to say 1.75 to the power of 14.6 gives me 3,534.72. Not the same, but good enough. So now that I have that common base, I'm going to replace this with 1.75 to the power of 14.6 equals 1.75 to the power of t over 2. And actually, I'm just going to put my rounding equal signs here because it is an estimation. And now I can set my exponents equal to each other. 14.6 is approximately t over 2. Cross multiply. 14.6 times 2 is 29.2. So that means in approximately 29 years from 1985. So 1985 plus 29 is 2014. We should surpass 1 million. So in 2014, the number of cell phone users should surpass 1 million. And if you're not confident in your answer, let's go back to our original equation and write 285 bracket 1.75 to the power of 29 over 2. And I got just a little bit under 1 million. So maybe it would even be safer to say in 2015 we'll surpass 1 million, just to make sure we are above. So I'm going to change that because I did my check. And there we are. That's it for exponential growth. So again, when you're writing your equation, you're always going to have your final amount equals your initial amount times your base to the power of the time over whatever that growth period is. And your base might be a factor like double, triple, quadruple, or it might be 1 plus whatever growth percentage was given to you. And once you have your equation, you can sub in values for time and punch into your calculator, or you can replace the final amount with a number and then solve the exponential equation with a common base or with guess and check. And that's it.